Welcome to our final lecture in this series on essential statistics. It's again on analyzing dichotomous data. Our table of different testing scenarios is almost complete by now. In this first part of the lecture, we will look at a test for dichotomous data if you have paired data. It's called McNamara test. In the last lecture, we covered the case of two independent samples. And one question that remained from that was, how do you compute a chi-square test for the differences between probabilities? So the chi-square test allowed us to determine whether two estimated probabilities are different enough to conclude that they are actually different. But of course, in many scenarios, the magnitude of this difference matters. And before we come to the paired test, we would like to show you how to compute confidence intervals for differences between probabilities in two independent samples. So we have sample 1, sample 2. We have y1 positive outcomes, n1 minus y1 negative outcomes, and n1 samples in total, and the same for sample 2. So we can again use our regularized estimates or biased estimates of P1 and P2. In this case, we use a slightly different version that just adds one fake sample to both of the two estimates, and use that to compute the probability, the sample estimate of the probability. We can then compute the standard error of the difference between these two probabilities in a similar way as we did in the case of continuous data, simply by taking the pooled variability between the two samples. Let's look at an example. And we had this example already in the last video about the reduction of migraines based on real or sham surgery. We found that there is actually, in this case, a significant difference between real and sham surgeries, with real surgeries leading to a successful outcome, which being more likely than in sham surgeries. Now, our estimate of P1, slightly regularized, is 41 plus 1 divided by 51 is 0.824. So 82.4%. And the estimate of P2 is 57%. So 16 over 28. Now the difference between these two probabilities is simply one minus the other, so 0.253, so 25.3%. To provide a confidence interval on this difference, we compute first the standard error of the difference, which is simply the pooled standard error of the two individual samples, which in this case is 0.101. So we can specify a 95% confidence interval as 0.253 plus minus 1.96 times 0.011, which is that the resulting confidence intervals is what you can read down here. So it's P1 minus P2 with 95% confidence is between 0.042 and 0.464. So we're 95% confident that the difference in probability is between 4% and 46%. Now we come to the case of the paired dichotomous data. It's not so apparent in this representation of the data, but imagine you're interested in the transmissibility of HIV from mothers to children. So, and we want to know whether older siblings have the same probability of being infected with HIV than younger siblings. This looks a lot like in the previous case where we had two experimental groups. But of course, in this case, there's a strong dependency between these two, because older siblings and younger siblings, they have the same mother. So we can represent the data in another way, which makes this more apparent. So we can say, does the older sibling have HIV, yes or no? And does the younger sibling have HIV, yes or no? In this case, these pairs here circled in red are also called concordant pairs, because in both individuals in the pair, they either both have HIV or not. And the green circled pairs are called discordant pairs, because those are the pairs that don't have the same outcome. Either one, the older sibling has HIV and the younger not, or the other way around. So the question that we want to ask is whether the probability that the older siblings have HIV and the younger siblings get HIV, whether that is the same or not. So to test that question, we use a test called Magna-Mars test. And the null hypothesis of that test is the probability of HIV infection the same for older sibling as for younger siblings? If you want to test that question, you also compute something like a chi-square statistic, but after some math, you can show that you actually just need the number of discordant pairs, numbers of discordant pairs to compute that statistic. So the only entries that matter, for this case is n to 1, so the number of siblings, for example, where the younger sibling has HIV but not the older sibling, or the other way around. And then you simply take their difference, you square it, and you divide by the sum. All the other entries for the chi-square test cancel out. We can do that for our example. This was our chi-square table, or our contingency table. And the two discordant entries are 17 and 18. So we simply compute 17 minus 18, compute the square, and divide by their sum. So that's 1 over 35, and that's 0.0286, which is really small. So if we compare that with our chi-square distribution with 1 degree of freedom, we find that the p-value in this case is 0.87, and thus we retain the null hypothesis. So our summary sentence could be, for example, that the data is consistent with the idea that HIV infection rate are the same for older and younger siblings. P-value of 0.87, n equals 228, Magna-Mars test. If you're not sure again what the difference is between paired data and non-paired data, or between the independent sample setting and the paired sample setting, I advise you to go back to the respective lecture where we covered this. Being able to exploit a paired design helps you to make more efficient statistical inferences from the data. The next topic that I would like to cover in this lecture is that of relative risks and odds ratio. These are probably terms that you have heard or read in the biomedical literature, and thus I think it's important to mention them here as well. Let's look at the following contingency table. We have smokers and former smokers and want to know about their risk of dying of lung cancer. So of the current smokers, 89 had lung cancer, while of the former smokers, only 37. And these values here didn't have lung cancer. So what we want to know is whether the risk for lung cancer is the same among smokers and former smokers. So P1, the probability of having lung cancer while being a smoker is 0.014 or 1.4%. P2, the probability of having lung cancer being a former smoker is 0.006 or 0.6%. So the relative risk just specify how much more likely it is to have lung cancer if you are a current smoker versus to have lung cancer if you are a former smoker as a ratio. So the relative risk is simply the ratio of these two probabilities. So it's computing that quotient, which is 2.25. That means it's 2.25 times as likely to have lung cancer when you're a current smoker. Before, we have simply expressed the difference in probability as an actual difference, not as a ratio, but this can also be done. What's maybe important to mention here is that both numbers are still quite small. There's yet another way that is called odds ratio. And the odds ratio is maybe less intuitive than the relative risk. So the so-called odds of an event are the probability that the event occurs divided by 1 minus the probability that the event occurs. And it probably helps to think of some examples. So if you have a probability of 1/2, that means that the odds are 1 to 1. So both events are equally likely. If you have an odds ratio of 1/4, that means in this case 1/4 divided by 1 minus 1/4, so 1/4 divided by 3/4, and that is 1 to 3. One event has a probability of 1/4. That means an odds that this event will happen of 1 to 3. You know this from betting, I presume. Then the odds ratio is simply the ratio of two odds of two events occurring. So the odds ratio theta is the odds of the first event divided by the odds of the second event. So in our example of the smokers here, the odds of having lung cancer while being a smoker is 0.147, if you just plug in the numbers. And the odds of having lung cancer when you are a former smoker is 0.006. You can see that the smaller the probabilities get, the closer the odds get to the probabilities themselves, because the numerator here, the denominator here, gets closer to 1. Then in this case, the odds ratio is simply the ratio of these two odds, and this is 2.265. Now, what is the relationship between the relative risk and the odds ratio? Often you will find that these yield very similar values, especially if the probabilities are small. This can also be seen by this equation that you can derive yourself as well. So the odds ratio is simply the relative risk times 1 minus p2 divided by 1 minus p1. And if both of these are small, then this is just multiplying by 1, and then the odds ratio and the relative risk are almost the same. So why have both terms, or what is possibly the advantage of being able to specify the odds ratio? The good thing about the odds ratio is that this can be estimated also when only row and column-wise probabilities are available, because an estimate of the odds ratio is n11 times n22 divided by n12 times n21, where these are the 4 entries, these are the concordant and these are the discordant pairs. So if we look at some fictitious data here for a cohort study of smoking and lung cancer mortality, this is different data than before. So what we did here was we did a cohort study in the sense that we enrolled 500 former smokers and 500 smokers and 500 former smokers. Of these 500 smokers, we found 7 had lung cancer and 493 did not have lung cancer, and 3 of the former smokers had lung cancer and 497 of the former smokers did not have lung cancer. But in both cases, 500 were observed. So we can simply compute the odds ratio as 7 times 497 divided by 493 times 3. And this is 2.35. What we cannot do is compute the relative risk, because this total is fixed. The same is true in a case control setting, where we fix the column totals. Among our 500 people with lung cancers, 273 were smokers and 227 were former smokers, and we can still compute the odds ratio. Okay, so coming back to our big table of different testing scenarios that we would like to talk about, there's just one testing scenario that is missing, and that is you have a continuous predictor and a dichotomous outcome variable, so this cell down here. One can use something similar to linear regression to analyze such data, which is called logistic regression. So let's say we have the following case. We have a study with 31 patients. Each of them has a certain tumor that has a different size, and we would like to know whether, depending on the tumor size, the tumor has already metastasized or not, whether that is predictive or whether there's an association between the two. So if we just plot the data, we can plot the tumor size on the x-axis, and then either zeros for does not have a metastasis yet, or ones here. Although we plot it like this, we cannot simply use regression. I mean, we could fit a line like this, but any of the values in between wouldn't mean anything. So what we do instead is we use logistic regression, and we fit a function that maps tumor size to the probability of having metastasized. To do that, we model the probability of the outcome variable being 1 as something called a logistic function. So this is where the name logistic regression comes from. So this is this function x divided by 1 minus x. And within the exponent here and here, we simply have a linear regression. So we have an offset, beta 0, and a slope, beta 1. The offset simply moves the logistic function about, and beta 1 determines how steep it is. We can fit these two data, so we can estimate these parameters of logistic regression. We don't go through the math here, but we can do it. And also do statistical tests for the significance of these coefficients, much like we did in linear regression. So in our case here of the data, what we did is we binned the data into several bins and computed the average probability. So for example, for these small tumors, the probability of observing a metastasis was 0.35 or so. And for these larger tumors here, around 6 centimeters, it was 0.8 or so. So when we fit this model to the data, this would be the predictions that it makes for the predicted probability. You can zoom out also a bit so one can see that the logistic regression prediction always saturates, it never goes back down. And it can have various different slopes and can have also different, it can be shifted along the x-axis. If you have such data in your research, let's say you apply different quantities of some treatment to your cells and count how many of them die, or for example in psychophysics this is also often used as a, say if you want to model the probability of detecting a visual grating as a function of the contrast, then you can also use logistic regression and test whether the independent variable, whether that modulates your predicted probability. Now, this scary slide puts everything together. This is a decision tree for which of the different tests that we covered in the lecture or that is covered in the book you should use to analyze certain your data in certain outcomes. Don't be scared by that. Most of that we actually did cover also in this course. So for example, the way you use that is if you have data that is a numeric response, a numeric predictor, then you use correlation. If you have a numeric response and a categorical predictor and two groups that are independent and normally distributed, then we can use either a confidence interval or a t-test, and so on and so forth. So with all of these different methods, I think we have covered a lot of essential topics that you need for your everyday life as a scientist in the life sciences or in whatever scientific discipline you work in. Of course, there's much more. But I also hope that you're now able, if you encounter a scenario which does not fit into any of these boxes, that you are able to recognize that because you know the assumptions that each of these boxes makes. And if you indeed are in a situation where none of the boxes that we covered fit, that you are able to go to the internet or go to an advanced statistics book and search for a good solution that actually covers your needs. Thanks a lot for the entire lecture and staying with us over this term.